All right, I want to talk about atomic structure. So first of all, we have to I have to tell you that existence of atoms is well established today. I think nobody has any doubts. There are atoms that make up all the existing matter, but it was not so, and it took a lot of effort to convince people of existence of atoms. Maybe I can just a couple of I can list a couple of names. If you have interest, you can go and check them out, but I'm not going to get into too much details. So existence of atoms, I think it was first, okay, of course there was ancient Greek and blah blah, I don't want to get into that, but scientifically, French chemist, I don't know how to spell him, but Lavoisier, and he was the first one to come up with something called conservation of mass in chemical reactions. And later, Dalton, he came up with law of, what is that called? Multiple proportions. Law of multiple proportions. So basically, these two guys saw that in chemical reactions, there was a counting balance before and after the reaction, which kind of hinted existence of indivisible constituents of the chemical elements that were giving rise to these reactions. And later, I think it was Avogadro. I think he's Italian, but I'm not sure. He, for example, said same P, same T, then same N. You probably know the ideal gas law. PV is equal to nRT. So this is basically due to Avogadro. If you have the same pressure and same temperature for a monoatomic gas or some molecular gas, you have the same number of atoms. And that's also the early work on the existence of atoms. But in the physics side, it was also related to the theory of gases, and I think there are other names, but I have to mention Maxwell. In parallel to his biggest work, which is electromagnetic theory, he was also working on thermodynamics and gases, and he was the one to formulate kinetic theory, again, which is based on existence of atoms, and also Boltzmann, which is the founder of statistical mechanics, which was also based on existence of atoms. And I think that was probably the reason he had the hardest time, right? People were telling him yeah, you are talking about these small things called atoms that nobody can see, but how do we know about their existence, right? People didn't just buy fancy ideas without any experimental proof. And also, I have to mention Einstein. In his golden year, he also had a paper on so-called Brownian motion. Today, we know it's also due to atomic structure. So basically, there's no doubt today that there are atoms, and we know they exist. And the question then is, what is the composition of atoms? And I have to remind you, atom, the word atom itself means the minimum indivisible units. And now we are thinking about the structure of minimum indivisible units. We are thinking about constituents of atom itself, which is the constituent of all matter. And of course, in an era of with the legacy of people who had strong doubts about the existence of atoms, we are going one step ahead and then talking about existence of internal structure of atoms. And the first work on this line of thought came from J.J. Thomson, which will be the starting point of our arguments and results for today. And J.J. Thomson discovered a particle with charge, which we later called it electrons. Actually, J.J. Thomson could identify the ratio E over M, and then he came up with like, okay, the atoms are composed of electrons, but we know the matter itself is neutral, so there has to be like an opposite charge, which we called ions. And he was thinking about matter to be like in so-called, I think, plum pudding model. There was like these positive energies, and there was like negative energies filling it just like a pudding, something like that. And after Thomson, I was like, okay, maybe I have to mention also Millikan. There's like a, okay, how do I spell his name? Millikan oil drop experiment established not E over M, but the charge of electron itself, which was the indivisible unit of electric charge. And after that, I think I have to talk about Rutherford. I think Rutherford was, I'm not 100% sure, but I think he was a student of J.J. Thomson, and he was actually skeptical about this model. And he was actually not skeptical, but he wanted to check the truth of this model based on experiments. So then we can now think about, let me atomic nucleus. Okay, there are other names, but the basic idea is use alpha particles. So alpha particles were a newly discovered form of radiation due to like some nuclear material that was discovered at the time, and they knew that they were like high energy particles with like very small size. And Rutherford suggested use alpha particles to probe internal structure of atom. So how do you do that? Like here's a kind of like a cartoon. You have this nuclear substance which radiates alpha particles in all directions. And you put this in like hopefully a chamber. And you put a hole in the chamber. This is called collimation. You collimate this, and you send these alpha particle beams on a material. Okay, and you want to see that the alpha particle just goes through, and this is like a tin foil. And the expectation is that all alpha particles just goes through. Why? Because here's a little bit of structure inside, and you have these plum puddings around, and there are like these electrons. So this alpha particle comes in, which is like a big truck, right? With very high energy. Protons are small particles, electrons are small particles. Nothing should just stand in the way of these like big, gigantic, and fast particles, right? Everything just should go through. So expectation is expect all alpha particles to go through undeflected, without any deflection. That was, of course, not the result. So basically the experiment is like you have put like a detector if you want, and you just, as a function of angle, right? So there's, for example, let me call a angle. So this is, for example, some angle theta. And as a function of this angle, we are trying to see how many alpha particles your detector receives. And the result of the experiment was something like that. Okay, oops. So this is, let me call this n of theta, number of alpha particles coming to your detector as a function of theta. And theta goes from 0 to like something like, let's say, pi, right? Maybe pi over 2, which is like, which is when your detector is right here, right? And actually, maybe theta goes to even like pi, because some alpha particles may even come back, right? There's nothing that, you know, if you are like an experimentalist with open minds, we can also anticipate that. So let me just put it pi. And the result was something like that. Yes, most of them went just undeflected, like this. But as you go to higher and higher angles, they were very small. Okay, here is very small. Very small, but non-zero number of alpha particles deflect significantly. Some even just go back, right? And he said that, for example, imagine you are firing like a bullet on a piece of tissue, and that tissue just returns the bullet back to you, right? That's not something you expect. And to explain that, Rutherford used, yes?
Why do they expect alpha particles to be undeflected?
Like because of this plum pudding model, right? J.J. Thomson came up with this plum pudding. So the alpha particle, now we know it is like a helium atom with all the electrons stripped, right? There's like 2 protons and 2 neutrons. Like there's like a heavy particle, whereas these there's like a single proton here, and electron is like 1,000 times lighter. And this is like a very fast, right? This is like about 8 MeV. It's like a very fast particle with very huge mass, and you are sending them to like basically little dust. And if you fire inside the dust, right, the bullet just passes through. And if at some point there's like even like a tiny bit of like deflection, you say that, okay, what I am firing at is not dust. There are like very big things in my target. So basically this, and his model was like, okay, it is not plum pudding. Okay, maybe I can write it here. He came up with a nuclear model where all the positive charge is in the center and all the electrons are in the cloud. And for this, he, okay, you can think about shooting your alpha particles to a target like this. In this case, you can still neglect electrons, right? Electrons are like 1,000 times lighter than protons, and an alpha particle is just going to just pass through the electrons. The only thing that matters is the ions, and you can model the ions, the interaction of ion and alpha particle with Coulomb interaction, and Coulomb interaction is 1 over 4 pi epsilon naught. Maybe I can say it like charge of alpha particle times Z times E is charge of ion. For example, for gold, for example, Z is equal to 79 for gold, and you divide this entire thing with R squared. So this is basically Coulomb interaction. Yes?
In those years, when they didn't
They actually didn't, right? Today we know alpha particles is just helium atom without its electrons. At the time they didn't know. All they did know was like it was like a massive radiation. There was like a huge mass, and it was like a very energetic. There was like 8 MeV energy of each radiation. But the inside structure I think was not known at the time. Initially, I mean later it was known, but initially it was not known. That's why they called it alpha particle. They didn't call it ionized helium.
What did they use to emit those alpha particles?
What did they use?
Emit those.
So I think they don't use anything. Like for example, there are different radioactive substances. I think one is polonium or polonium, or maybe some is uranium. And each has its own characteristic emission, and each has like alpha particles, all beta particles, all kind of radiation, and the energies are also different. You can like take one substance, look at the emission, how much damage it makes on its environment, and you can change it, like put for example uranium, and you can look how much damage that one does, and you can say like the alpha particles coming from the sample 1 is likely to be like more energetic than alpha particles coming from the second sample. And of course, this is like a little bit cartoon, but more systematic studies know today we know it's like about 8 MeV, which is a huge energy. So the key is about this is like this process is just a Coulomb interaction, and this is basically scattering from Coulomb potential. Because electrons are very light, right? Like proton is 1,000 times heavier than an electron, right? And no, they are the same, but the mass of electron is so light. Electron is just going to you are going to blast off the electrons. Nothing will come in your way, right? The main thing will be the heavy nucleus. Of course, high order effects are also there. Electron is also there. But the primary contribution to your result is going to be from the ions. We are trying to get the most important effect. And so this is classical scattering of alpha particles from a Coulomb potential. And Rutherford actually sit down and calculate that, which your book also has. Let me just write the results. So he found n of theta was equal to, maybe there are some unnecessary factors that I don't care about. Let me just write the ones I care. It is proportional to z squared e to the 4th divided by 4th power of sine theta over 4. Okay. So this one is just calculation of scattering cross-section from like a Coulomb potential. If you haven't done that, that's a little bit of technical calculation, but your textbook has it. And I think at some point, maybe in classical physics, they are supposed to show you that you need to know how to set up a scattering problem, and you need to know how to calculate the so-called scattering cross-section. And that's what this quantity is. But I think for now it's not important. For us, this formula comes from existence of a nucleus with very large mass and very large charge. Okay, this formula explained experiment to high precision. So basically, if you have like experimental data like these dots, and the theory is just these lines, they just overlapped. And different substances, for example, rather than gold foil, for example, you can use aluminum foil. All you need to do is like you see the Z is going to change, and it's going to just shift let me write it like a bit like different color. So this is, for example, like it's going to be a shift, but it's also going to be, so this is aluminum, this is gold. Any questions? Maybe I can just tell you about one more thing. Yes.
Gold up,
Gold?
up indigo.
Uh-huh.
Aluminum is high, like
Oh, yes, you are right. So this is aluminum, this is thank you. Good job. Okay. So when alpha particles start to penetrate nucleus, we expect deviations from Rutherford formula. Why? Why do we expect deviations from Rutherford formula when you start to probe the internal structure of nucleus? Right? There are like neutrons, there are protons, but what is the basic assumption that is violated? Huh? The atomic mass is also constant, but there is another thing, right? When you start to like probe the internal structure, it's like no more like a point particle, right? Like it's like at some point, exactly like you said, you start to see protons and neutrons, but it is not a point particle anymore. You basically like an extended object. And when this happens, like when alpha particles start to penetrate the nucleus, you expect to see deviations from this formula, right? And there are two ways to do this. One way is to increase the energy of alpha particle, right? That's what they are doing in accelerators. You just like go to higher and higher and higher energies to go to like smaller and smaller and smaller structures. But the another approach is like, okay, alpha particles I cannot control, right? They are given to be 8 MeV. Maybe I can like choose another nucleus. Rather than gold, I can choose aluminum. And whenever I see the deviations, I can say, okay, that's when like we started to probe the nuclear structure. And from here, okay, when this happens, you can compare kinetic energy of alpha particles with potential energy due to nucleus, and it is going to give you an idea of the size of the nucleus, right? So whenever this, okay, here's the picture. So I have this nucleus, and alpha particle comes in, and it deviates back. And here there is only kinetic energy. Here there is only potential energy. Here only kinetic energy. It's coming from minus infinity. Here I have only potential energy. And if I equate kinetic energy to potential energy, it's going to give me like an idea of this so-called d min, which is going to be an upper bound of the nucleus, right? So kinetic energy initial is going to be equal to potential energy at the return point, and this is going to be 1 over 4 pi epsilon naught Ze times 2e is the charge of alpha particle, and it's going to be divided by, let me call this d min. So this is 8 MeV. So this is, I don't know, for aluminum For some reason, I calculated it for gold, but I think you can also calculate it for aluminum. For gold, Z is 79. E is electron charge. Epsilon naught is a constant of nature. From here, you can find d min, which is, I found, 3.0 times 10 to the minus 14 meters. Okay, so this is, at least in this course so far, the smallest distance we have come to, and this is the actually an upper bound to the size of nucleus. Okay. Any questions or any comments? Now we can think about electrons orbiting this small size nucleus. Let's consider electron orbits. So consider an electron orbiting a tiny nucleus. Let's start with classical physics. So here is, let's say this is plus E, and there's like minus E, and there's like some radius of orbit. Let me call this R. And okay, this is V. We know when in the circular motion, the balance is like between like this central force, right, and the Coulomb interaction. When F Coulomb is equal to mv squared over R, this is equilibrium orbit, and F Coulomb is 1 over 4 pi epsilon naught E squared over R squared. And let me cancel that with that, and I'm trying to find V. V is going to be what? E squared over 4 pi epsilon naught mr, right? And I need to take the square root, and if I take the square root of E, I have this. Okay, good. Now kinetic energy is 1/2 mv squared, and potential energy is minus 1 over 4 pi epsilon naught E squared over R, and total energy E is equal to 1/2 mv squared minus 1 over 4 pi epsilon naught E squared over R. And from here, I can substitute this, right? This is going to be 1 over 2 m E squared over 4 pi epsilon naught mr, cancel m with this. This is 1 over 4 pi epsilon naught E squared over R. So this is 1/2 minus 1 is going to be minus 1/2, 1 over 4 pi epsilon naught E squared over R. Basically, total energy is half of the Coulomb energy in equilibrium orbit. This is half of Coulomb energy, which is a handy thing to remember if you want to do quick calculations. But there is like a problem with this picture. So okay, from the Rutherford result, we know there's like a nucleus, and we know there are like electrons from J.J. Thomson. So and these light electrons are orbiting like a heavy nucleus, but there is a problem with this. So problem. What is the problem? I think everybody knows about that. A charge circling a nucleus is not classically something that's supposed to be stable, right? What is the problem here? Yes, why would they fall out? What is the, yes? They radiate. So when do we expect radiation in classical physics? Exactly. So in classical physics, classically, acceleration means radiation. Radiation means loss of energy. Loss of energy means these electrons gradually losing their energy and falling to the center, right? So classically, because circular motion is a motion with non-zero acceleration, right? So we have this condition, and electrons are charged. So we also have the charged particle in an acceleration that's also satisfied. So there has to be a radiation. However, empirically, atoms in their steady state, atoms do not radiate. Right? They are like stable forms of matter. If it's stable, it shouldn't radiate, because if you are radiating, you are losing energy, and eventually you should dissipate. So that was the first problem. But there was also a second problem, which is completely, of course it was related, but it was found in parallel to this. There is also so-called atomic spectra, right? So that was an empirical result, and this picture didn't explain why we should have a result like this atomic spectrum. Now I want to mention what this atomic spectra is, and maybe after that we can take a break. So let's talk about. Okay, I think spectra is plural form of spectrum, and different atoms have different characteristic spectra. And the way it was found is very simple. Suppose you can apply very high voltages, and suppose you are doing this, you have a gas, dilute gas inside your vacuum, and you apply a high voltage, and the result is radiation comes out. And from here you can say, for example, I want to do the double slit experiment, and they're actually they don't do the double slit experiment. They use so-called diffraction grating, which is kind of like a double slit experiment, and as a result they have some pattern, which is the spectrum. And this first spectrum was characteristic of the gas used. So what this means is if you use for example hydrogen, you have one spectrum. If you use helium, you have another spectrum. If you have neon, you have another spectrum, and so on. And there were a bunch of, for example, here's the result for hydrogen. So you had one line, this is called H, okay, this is wavelength. You had one spectral line which is called H alpha now, 656.3 nanometers. You had another one at what is called H beta, was equal to 486 nanometers. and all the way, and this spectrum was terminating at some point, like, okay, all the way to here, and the last result was at 364.6 nanometers. Luckily, these are all in visible range, so you could see these lights. And the empirically, okay, here's the empirical result. Empirical. This was known way before anything about quantum was even like in mentioned. It was like mid 18th century, and the relation was something like that: 1 over lambda was equal to some constant times 1 over 2 square minus 1 over n squared, and n was equal to 3, 4, 5, dot, dot, dot. And R, which was later called like Rydberg constant, was known to be 1.097 times 10 to the 7 m 1 over meter, which was, okay, maybe in nanometer 0.01 097 1 over nanometer. And for example, here H alpha was obtained by putting n is equal to 3 here, and H beta was obtained by putting n is equal to 4, and so on. So this is what we call today Balmer series. Balmer series. And later there were other like other emissions that were not indivisible. For example, there were like Lyman series, where 1 over lambda was equal to r times 1 over 1 square minus 1 over n squared, and n was equal to 2, 3, 4, dot, dot, dot. There was Paschen series, 1 over lambda was equal to r times 1 over 3 square minus 1 over n square, n was equal to 4, 5, 6, dot, dot, dot. There was bracket series, bracket, so this becomes 4, and there was also fund series. So this 4 became, I think, 5. Okay? And the question is, how atomic structure gives rise to such emission spectrum. Maybe we can take like here a 5-minute break, and when you come back we can talk about Bohr model and see how it explains the emission spectrum.